You think you're made of particles, electrons, protons, neutrons, solid little things bouncing around, combining to form atoms, molecules, you. That's what they teach in school. That's what the diagrams show. Little balls of matter, stacked together like building blocks. But here's the uncomfortable truth that physicists have known for nearly a century. Particles don't exist. Not really. Not in the way you think. What we call particles are actually disturbances in fields. Invisible, omnipresent fields that fill every cubic centimeter of space throughout the universe. You're not made of things. You're made of patterns in fields. And I know that sounds abstract, maybe even meaningless. What does that even mean? Patterns in fields? But stay with me. Because once you understand what fields really are, everything about reality shifts into focus. Everything makes sense in a way it didn't before. Before we can understand why fields are fundamental, we need to understand what a field actually is. And it's simpler than you might think. But also stranger. A field is just a value assigned to every point in space. Every point. No exceptions. Imagine a weather map showing temperature. At every location, every city, every coordinate on the map, there's a temperature. 10 degrees here, 20 degrees there, 15 degrees over there. The temperature field tells you, at this point in space, the temperature is this. At that point, it's that. The field is the entire collection of values, one for each point in space. Now, extend this concept to physics. The electromagnetic field assigns values to every point in space. Values that tell you how much electric force and how much magnetic force a charged particle would feel if it were there. The gravitational field does the same for mass. It tells you how spacetime is curved at each point, how a massive object would move if it were there. Quantum fields, electron fields, quark fields, photon fields assign quantum values to every point. Values that determine the probability of finding a particle-like excitation there. These aren't abstractions. These aren't mathematical conveniences we invented to make calculations easier. These fields are the actual substance of reality. Everything else, particles, forces, matter, energy, is just the fields doing what fields do. Vibrating, interacting, creating patterns we perceive as solid objects. And this bothers me, because the word field sounds so abstract, so mathematical, like something made up by physicists. But fields are more real than particles, more fundamental than atoms, more concrete than the matter you think you're touching right now. The history of physics is a story of replacing things with fields, of discovering that what we thought were objects are really patterns. First, we had particles, tiny solid objects bouncing around, Newton's corpuscles of light, Dalton's indivisible atoms, little hard spheres of matter. Then we discovered forces acting at a distance, gravity, electromagnetism. How does the sun pull on the Earth across 150 million kilometers of empty space? Newton himself was troubled by this. He wrote that action at a distance was absurd, that there must be something mediating the force. The answer turned out to be fields. The sun doesn't reach out and grab the Earth. Instead, the sun's mass creates a gravitational field, a distortion in the geometry of spacetime itself, and the Earth responds to the field at its location. The field mediates the interaction. It's not action at a distance. It's local action in a field that extends everywhere. Then came the quantum revolution, and everything got stranger. Particles started behaving like waves. Light behaved like both a wave and a particle. Electrons created interference patterns, as if they were spreading out and passing through multiple paths simultaneously. The double-slit experiment shattered any simple particle picture. Send one electron at a time through two slits, and over time, it builds up an interference pattern, as if it went through both slits, as if it were a wave. But detect which slit it goes through, and the interference disappears. It acts like a particle again. What's going on? The resolution came in the 1920s and 30 seconds with quantum field theory. And this is where everything changes. What we call an electron isn't a little ball of charge. It's a localized excitation in the electron field. A ripple, a standing wave, a persistent pattern in a field that exists everywhere. The electron field fills all of space. At most points, it's in its ground state, the vacuum, the lowest energy configuration. But poke it with enough energy, and you can create an excitation. We perceive that excitation as an electron. Add more energy, create more excitations, get more electrons. They're not separate objects that were created out of nothing. They're vibrations called into existence, like plucking strings on a cosmic instrument. When you detect an electron at a particular location, you're measuring where that field excitation happens to be at that moment. You're sampling the field. The electron field is always there. The excitation is what comes and goes. So why do particles seem so particle-like? Why do they act like discrete, localized objects if they're really just field vibrations? Quantum mechanics. That's why. The fields are quantized. They can only vibrate in specific ways, with specific energies. Just like a guitar string can only produce certain notes, because only certain standing waves fit on the string, quantum fields can only excite in certain patterns. The smallest possible excitation has a definite energy, a definite momentum, a definite charge. We call that a particle, but it's not a thing. It's a quantum of excitation, a minimal disturbance in the field. It has particle-like properties, localized position within uncertainty limits, definite charge, specific mass, because those are properties of how the field can be excited, not because there's a little ball hidden inside. When a particle moves, the field excitation propagates. The pattern of vibration shifts from one region to another. When particles collide, field excitations interact, merge, split, transform according to the equations governing those fields. When a particle decays, one field excitation disappears, and different field excitations appear. Energy is conserved, charge is conserved, momentum is conserved, but nothing is turning into something else. Fields are just rearranging their excitations. The double-slit experiment makes perfect sense in this picture. Finally, after a century of confusion, the electron field propagates through both slits. It's everywhere, after all. The field interferes with itself, creates a pattern of high amplitude in some places, low amplitude in others. When you measure where the electron is, you're sampling the field, and you get a result weighted by the field's amplitude squared at each point. The interference pattern emerges from the field dynamics, not from particles doing something mysterious, not from waves collapsing, just fields being fields. And I find this deeply satisfying. The mystery dissolves when you stop thinking about particles and start thinking about fields. How many fields are there? How many fundamental fields fill the universe? In the standard model of particle physics, we have about 25 fundamental fields, one electron field, and separate fields for muons and taus, the heavier versions of electrons, 6 quark fields, up, down, charm, strange, top, bottom, 3 neutrino fields, 1 photon field, the electromagnetic field quantized, W and Z boson fields for the weak force, 8 gluon fields for the strong force, 1 Higgs field, the field that gives other fields their mass properties. That's it. That's the complete list as far as we know. Everything in the visible universe, every atom, every molecule, every star, every planet, every living creature, is made from excitations in these approximately 25 fundamental fields. You are a pattern in these fields. Your electrons are excitations in the electron field. Your quarks, which make up your protons and neutrons, are excitations in quark fields. The photons bouncing around inside you, mediating electromagnetic interactions between your electrons and nuclei, are excitations in the photon field. When fields interact, when an electron field excitation encounters a photon field excitation, they follow precise mathematical rules. Quantum electrodynamics describes how electron and photon fields influence each other. It's the most precisely tested theory in all of science. Predictions match experiments to 10 decimal places. Quantum chromodynamics describes quark and gluon field interactions, how quarks bind together inside protons and neutrons.
The electroweak theory unifies electromagnetic and weak interactions. These aren't just models. These aren't approximations or convenient fictions. The fields are real as anything in physics. Here's where it gets truly strange, where the picture becomes even more bizarre. Even empty space isn't empty. The fields are still there, filling every point. And quantum mechanics says these fields never stop fluctuating. Even in its lowest energy state, the vacuum, a quantum field jitters and vibrates. Virtual particle-antiparticle pairs constantly pop into and out of existence, borrowing energy from the uncertainty principle for impossibly brief moments. These aren't real particles you can detect and isolate, but they have measurable effects. Real, observable, testable effects. The Casimir effect. Place 2 metal plates close together in vacuum, and they're pushed together by a tiny force. Why? The plates restrict which vacuum fluctuations can occur between them. Only certain wavelengths of field vibration fit. This creates an imbalance in quantum field vibrations that manifests as a physical force. We've measured this. It's real. The Lamb shift. Energy levels in hydrogen atoms are slightly different than simple quantum mechanics predicts. Why? Because the electron doesn't just interact with the proton, it interacts with the vacuum fluctuations of the electromagnetic field surrounding it. The jittering field shifts the electron's energy levels. We've measured this too, to extraordinary precision. Hawking radiation. Near a black hole's event horizon, vacuum fluctuations can become real particle pairs. One falls into the black hole, one escapes. The black hole loses mass. It radiates away due to quantum field behavior in extreme spacetime curvature. We haven't measured this yet. Black holes are too far away, and the effect is too small, but the theory is sound. The vacuum is a seething foam of quantum field activity. Space isn't a passive stage where particles perform. It's an active player, a dynamic web of interacting fields that never rests. And this is strange when you think about it. Empty space isn't empty. It's full of fields fluctuating, vibrating, creating temporary excitations that vanish before they can be observed. The universe, at its most fundamental level, is restless, never still, always fluctuating. Forces too are field interactions. This is crucial to understand. Electromagnetism isn't a force between charged particles. It's an interaction between the electron field and the photon field. When two electrons repel, they're not pushing on each other directly. Their electron field excitations interact with the photon field. They exchange photon field excitations, virtual photons, and this interaction alters their trajectories. The strong nuclear force binding quarks inside protons, that's the quark fields interacting via the gluon fields. The weak force causing radioactive decay, that's quark and lepton fields interacting via W and Z boson fields. Even gravity, in the quantum picture, might be the curvature of spacetime interacting with matter fields via a hypothetical graviton field. Though we don't yet have a complete quantum theory of gravity, that's the great unsolved problem in physics. Every interaction in nature is really a field interaction. Fields overlap, influence each other, exchange excitations, create patterns of correlated behavior. What we perceive as forces are the mathematical consequences of these field dynamics. You don't push on a door by making your particles touch door particles. Your electron field excitations get close to the door's electron field excitations. The electromagnetic repulsion, mediated by photon field interactions, prevents the fields from occupying the same state. That manifested resistance is what you feel as solidity, as pushing, as contact, but nothing ever touches. Fields interact, creating the illusion of contact, the sensation of solidity, the experience of pushing and being pushed. And once you understand this, you realize that everything you've ever touched was an illusion in a very real sense. Why is the universe built from fields rather than particles? What makes fields so special? I've thought about this, and here's what I think, though I could be wrong. Locality. Fields naturally handle the problem of action at a distance. Every interaction is local. Fields only interact with other fields at the same point in space. Information propagates through fields at finite speed, usually the speed of light. No instant action at a distance. No violations of causality. Quantum mechanics. Fields naturally incorporate wave-particle duality. A field can have wave-like behavior, smooth continuous variations, and particle-like behavior, quantized excitations. The wave-particle duality isn't a contradiction. It's not a mystery. It's a natural feature of quantum fields. Conservation laws. When fields interact, they automatically conserve charge, energy, momentum, and other quantities because these are built into the field equations. You don't need to separately enforce conservation. It emerges from the symmetries of the fields, from Noether's theorem, and perhaps most importantly, universality. There's only one electron field. One field filling all of space. Every electron in the universe is an excitation in that same field. This explains why all electrons are identical. Same mass, same charge, same properties. Exactly identical. They're not separate objects manufactured to identical specifications. They're vibrations in the same universal field. And the field dictates what properties its excitations must have. This is profound. And it's not something particle theories can easily explain. But here's what bothers me. What we still don't understand. Why these fields? Why these particular 25 or so fields and not others? Why do they have the properties they have? The masses, the charges, the interaction strengths? We don't know. We can measure these values. We can build the standard model around them, but we don't know why. Maybe there's a deeper theory, string theory, loop quantum gravity, something else. A theory that explains why the fields are what they are. Or maybe these are just the fields that exist. And asking why is like asking why the universe exists at all. I don't know. And that's okay. That's where the mystery lives. Look around you. Everything you see is fields, the light hitting your eyes, photon field excitations, electromagnetic field vibrations at specific frequencies. Your eyes, electron field and quark field patterns organized into atoms, molecules, cells, complex structures built from field excitations. Your thoughts, electromagnetic field patterns propagating through neural networks made of field excitations. There are no particles. There are no solid objects. There is nothing but fields, invisible, omnipresent, dynamic fields filling all of space, vibrating in intricate patterns that give rise to the appearance of a material world. You are not made of things. You are a pattern of disturbances in fundamental fields, a temporary configuration of excitations that maintains itself for a while, metabolizes, reproduces, thinks, before eventually dissipating back into the quantum foam. And yet, paradoxically, this makes you more connected to the universe, not less. You're not separate from the cosmos. You're not an isolated collection of particles somehow distinct from everything else. You're a localized expression of the same fields that constitute everything else. The electron field excitations in your body are the same field that extends to the most distant galaxy, 13 billion light-years away. The same field. You are continuous with all of existence, made of the same fundamental substance, connected through fields that know no boundaries. Fields are the only thing that exists. Everything else, particles, forces, matter, even space and time as we experience them, is just fields doing what fields do. Vibrating, interacting, creating patterns, creating the illusion of separate objects, the illusion of solidity, the illusion of you and me and everything we perceive. Welcome to the real universe. This is what Richard Feynman spent his life trying to understand. Not just the mathematics of fields, though he revolutionized that, but what it means. What it actually means that we're patterns in fields, not collections of particles. He looked at the equations and asked, what is this really telling us about reality? Not just how to calculate answers, but what is? And the answer, as strange as it sounds, is fields. Just fields, all the way down.